Hi viewers, welcome back to my tutorial class. Today I am going to discuss a problem on composite bar. A composite section consists of a steel rod of 140 mm diameter and an outer brass tube of internal diameter 140 mm and external diameter 160 mm, rigidly fixed over the steel rod. The composite section has a length of 600 mm and it carries an axial load of 400 kN. Find the stresses produced in each material and the load carried by both the materials. Take E of steel as 2 into 10 raised to 5 Newton per mm square and E of brass as 1 into 10 raised to 5 Newton per mm square. So you have a composite bar which consists of a steel rod of 140 mm diameter, and you have a brass tube which has inside diameter 140 mm and outside diameter 160 mm. So inside the brass tube you have the steel rod, and which exactly fits inside because the steel rod is 140 mm diameter, whereas the brass tube inside diameter is 140 mm. So the steel rod is exactly inside the brass tube, and this section has 600 mm long, and it is subjected to an axial load 400 kN. It's not mentioned whether it is tensile or compressive, but it is an axial load. It can be either tensile or compressive. Now we need to find out the stresses produced in both the materials when this load acts and the load shared by both the materials. Young's modulus of both the materials are given. I have shown the composite section. So this is a steel rod. Its diameter is 140 mm, and this steel rod is inside the brass tube. Brass tube inside diameter is 140 mm and outside diameter is 160 mm. So I have written this, all the data given. Diameter of the steel rod is 140. Outer diameter of the brass is dB0. B stands for brass and O stands for outside. So dB0 is 160 mm. So this diameter is 160 mm and inside diameter of brass is 140 mm. Now axial load is 400 kN. It's equal to 400 into 10 raised to 3 Newton. Length is 600. This length is 600 mm. We are not going to utilize this data. It's an excess data given. Now Young's modulus of steel is given and Young's modulus of brass is given. Now you can find out the area of cross section of each material. So steel is having a diameter 140 mm. So the cross section area, this portion, the area is pi by 4 into diameter square, which will give 15,393.8 mm square. Also the brass portion, which is the hatched white portion, so that area is annular area, that is pi by 4 into 160 square minus 140 square. So the total area, total circular area, that will be pi by 4 into 160 square. You need to subtract this area, that is pi by 4 into 140 square. Pi by 4 is common, so pi by 4 into 160 square minus 140 square, which will give the areas 4,712.39 mm square. So you got the area of cross section of both the materials. Now let us come to the deformation of the composite section. So the deformation is going to be equal because they are rigidly fixed. There is no independent deformation. So when it's subjected to axial either compressive or tensile load, and they cannot deform independently. Both will deform equally. So if it's a compressive load, both will decrease its length by the same amount. So the decreasing length or increasing length are same, and this composite section is having 600 mm length, and both the materials are of same length. So deformations are same, lengths of both the materials are same. So strain must be equal. Equal deformations in equal length. So strains induced in the materials has to be same. So you can write sigma S by ES is equal to sigma B by EB. This is strain. Stress by Young's modulus is strain. If you multiply with the length, you will get the deformation. But lengths are equal. So if you put LS here and LB here, LS is equal to LB. Length of steel rod and length of brass rod are same. So that will cancel out. So strains induced in both the materials are equal. So you can write sigma S by ES is equal to sigma B by EB. So you get sigma SS ES by EB into sigma B. Now you can substitute for ES and EB, which will give 2 sigma B. So sigma S is 2 times sigma B. So stress induced in steel will be always 2 times greater than the stress induced in brass, irrespective of the magnitude of the load. Whether you apply 100 kilonewton or 200 kilonewton or 400 kilonewton, the stress induced in steel has to be 2 times greater than the stress induced in brass for these values of Young's modulus. So you understood the relationship between stresses induced in both the materials. Now you can use the second equation for composite bar. That is, the total load has to be carried by both the materials together. So PS plus PB is equal to P. So load taken by steel plus load taken by brass, that is equal to total load. So PS you can write it as sigma SAS, and PB is sigma B AB is equal to P. And now you can substitute for area of steel and brass, and also you can substitute sigma S as 2 times sigma P. So 2 sigma B and AS we have substituted, and AB also we have substituted. So you can easily solve this for sigma B. So only one unknown sigma B is there. Right hand side is the load, and load I substituted in Newton, and this area is in mm square. So you get sigma B in Newton per mm square. So stress in brass you got. Now once you get the stress in brass, we have this relation. Stress in steel is twice that stress in brass. So 2 times of this value is 22.54 Newton per mm square. So you got stresses in both the materials. Next you have to find out the loads. Loads in each material is PS is sigma SAS and PP is sigma BAB. So you can use that equations to find out the load. So PS is equal to sigma SAS. Stress in steel is known now, and area is also known. You can calculate the load taken by steel rod. So stress is 22.54 Newton per mm square, and this is in mm square. So you will get in Newton. So you have to divide this by 1000 to get the value in kilonewton. So you can always write in kilonewton because this is a large value. Now PB you can calculate as sigma B AB, or the total load is known, and we know that the load shared by steel. So remaining has to be taken by brass. So the total load minus the whatever load carried by steel will give the load shared by brass. We can also use sigma BAB to calculate the load taken by brass. So you got the load taken by both the materials, and also we got the stresses. That's all for today. Thank you for watching.